In the Northern Hemisphere, the flu season typically runs from early December through March. The Southern Hemisphere is the mirror image of this pattern. The flu season there runs from May through October. 80 years ago, whooping cough was a summer epidemic of children in the Northern Hemisphere. Today, most children receive the 3-dose DPT, diphtheria, pertussis, tetanus vaccine, which protects against infection for several years, and whooping cough is now a fall epidemic in teenagers. Seasonality seems to be the norm rather than exception for diseases with relatively short infectious periods. The cause of the seasonality is relatively obvious in many cases. Vector-borne infections, for example, circulate most widely when vectors are most abundant. Since many vector populations are influenced by temperature, transmission often peaks during the summer in temperate regions. Waterborne infections are often also driven by environmental conditions. Cholera in Bangladesh, for example, shows 2 peaks per year. A smaller epidemic in the spring, just before the monsoon, followed by a larger epidemic in the fall towards the end of the monsoon. The thought is that these are associated with periods when the environment is most favorable for the Vibrio bacterium responsible for the disease. Environmental factors are also likely to be associated with the winter peak in influenza and the historical summer peak of whooping cough. Influenza viral particles survive longest when the absolute humidity is lowest, as it is during the winter in temperate regions. Thus, transmission is most robust during this period. The bacterium that cause whooping cough, in contrast, prefer warm periods with high relative humidity, the summertime. When seasonality is determined by environmental factors, we call it environmentally forced disease dynamics. Surprisingly, the current fall peak in whooping cough is not associated with the environmentally most favorable season for the pathogen. It does, however, coincide with peaks of several other respiratory pathogens. Instead of being driven by the environment, this seasonality reflects seasonal changes in contacts among hosts. Contact rates among school-aged children are usually many times greater during the school term than during vacation time. In addition, new cohorts of children, many who are susceptible, enter into schools each fall. As a consequence, we get seasonal outbreaks fueled by a lot of mixing of susceptible and infected individuals in a close contact environment. We call this type of seasonality term time forcing because of its association with opening and closing of schools. We see similar behaviorally associated seasonality in measles outbreaks in West Africa. There, however, contact rates are not molded by schools so much as the urban-rural seasonal migration associated with subsistence agriculture. During the wet season, contact rates are low because people are spaced out in rural communities. During the dry season, contact rates are high and transmission is robust because many families congregate for work in peri-urban settings. Seasonality in most infectious diseases reflects a combination of environmental and behavioral forces.